Thank you for sticking up to the last minute to the meeting. And we hope will be beneficial to us, to all of you, as I benefit in the last 2 days and learning a lot. And I hope I can use many of your slides in my green chemistry classes, because we just have started the courses in green chemistry, and I hope I can push and introduce some of the technology and the chemistry to the classes. And I am from Chung-Hsin University, close, but Chung-Hsin University in the central Taiwan. That is in south of Japan and 100 kilos from the continental Asia, China. And although it's a small island, the population is very dense. And the island have electronic chemistry and petroleum chemistry. But you will hear in last 2 weeks, there is an explosion in Kaohsiung in Taiwan that killed about 30 people, and the whole street, the pipeline from the petroleum company to the polypropylene plant exploded. And the whole street was exploded and killed many, many people, and also the car and the houses. And that's really affecting the chemical industry image in Taiwan. And that is part of the reason I go back to Taiwan after I retire from Dow Chemical Company. They use me because they're hoping the chemical industry can benefit from my expertise in polyurethane, especially in the central part of Taichung. There is a polyurethane chemistry, and we try to develop the green part of adhesive. And as you know, the PU is 100 billion business, and the problem is associated with diisocyanate chemistry that is very reactive, and associated with phosgene, that is poison gas. And so here my topic will be on the green part of the process to come up with a solution to the new process. And many previous speakers already elaborated on this green engineering principle and this green chemistry by the Anatas and Warner, so I won't go through again. But the important thing is in the last several paragraphs, non-phosgene allowed and non-isocyanate allowed. Prevent using the toxic chemical and prevent using the reactive chemical. But we can making the polyurethane or polyurea with a benign chemical. That is the topic of my research and topic of my presentation also. And that you can see, go through this most important isocyanate product called MDI, the methyl diphenyl isocyanate. You can see from beginning, you are using the concentrated sulfuric acid, the nitric acid. That's not very friendly. And the formaldehyde is toxic, and the phosgene is even worse. So you can see the whole process of making the MDI is difficult. And actually you have to have, just like Dow Chemical have an integration site that from monoxide and also the chlorine, all in the small quantity, then making the phosgene and then leading to the isocyanate plant. And so that is difficult to do in Taiwan. It is impossible. And actually, when the buyer tried to come to Taichung to make a plant, the whole town, Taichung town, they become revolt and have the demonstration, and then the plant eventually go to mainland China. So this is what happened. And as you can see, the most important part is making the amine part, and they're using phosgene to convert it to isocyanate. And from the isocyanate yield, still the most important part is 4,4 MDI. The 4,4 MDI. The other part is go to the insulation part of the polyurethane usage. The 4,4 MDI is then using making PU, that is elastomeric or plastic or the other important thing. So that is 4,4 plant is the largest part of the MDI business. And the problem associated with that, as you can see, a safety problem because you are dealing with phosgene. And you're making 2 more of HCl gas every isocyanate function. So HCl gas, you need to management, and it's corrosive, difficult to take care of it. And your product, MDI, and then you have a chloride impurity in it that affecting the reactivity also. So as you can see, there is a cost and safety problem associated with it. And so in last 40 years, there is a non-phosgene developed. The development is come to the formation of this carbamate. The carbamate can use the carbonylation process. The carbonylation making the carbamate, and then you pyrolyze the carbamate without using the phosgene in the process, then you're making the isocyanate. So this is the process. I think it's acceptable. But this is another carbonylation agent you can use. From carbon monoxide that used by Orling in 1960. I'm sorry. This is not good enough. This one? Okay. Okay, let me try. Oh, this is much better. So Orling in 1960 using the carbonylation is carbon monoxide, but that's still is a poison gas. And then the alcohol using the reductive amination to go through the carbamate and making isocyanate. That is 1970. And then Asahi using a similar process, but we call the oxidation carbonylation. And then followed by urea, followed by carbonate. This carbonate is when I was down working on it, so I know. And the Monsanto using carbon monoxide, and the current using this process. And this is the 1974 that seemed to be the most important year that the ARCO proposed this workable process. And at that time, I'm working in Upjohn, that is the MDF company, and we are very, very worried about this process going to substitute the phosgene. So we studied this chemistry. Unfortunately, we found out the selenium catalyst is a poison and difficult to recover. And find out this that last finish is need to have a 250 degrees C to pyrolyze to making the isocyanate is difficult. And then 4 years later, the Asahi come up with a better process. The difference is they're using the ethyl instead of methyl, and the reaction here is much more efficient. And the other thing is what they are using is the carbonylation using palladium seems to be working much better. And they have scaled up the plant and then come to now to selling this technology. And then there's more recent, they have another carbonylation whereby in formic acid to making the formamate. The formamate chemistry, and then you exchange with carbonate. And this carbonate chemistry then become important in my group, and we found this will be a very nice chemical to use. And the other thing urea process was found in IPDA, that means in aliphatic area, aliphatic amine area. That is more basic, the amine. They can using that to make it work on making the IPDA isocyanate. So, by summarizing all the chemical, you can see from phosgene is the most reactive. And then they have some other substitutional compound. It also carbonate can be used. It's a green compound, but it's very expensive. And this diphenyl carbonate is a medium. And then you can see the urea is more or less reactive, and dimethyl carbonate that's used by the other company is less reactive. And we have chosen this compound as a major substitute in our carbonylation reaction. And our approach, as you can see, is making the diamine and then carbonylation to get diphenyl carbamate. And then we have two ways: by go through the pyrolysis to making MDI, or we can go through here as the intermediate and do the transfer esterification directly to making the polymer. That's without isocyanate and without the phosgene. So our way of thinking is we have the knowing that epoxide can convert it to carbonate, cyclic carbonate. Cyclic carbonate can exchange with the phenol to making diphenyl carbonate. And that happened, Taiwan have this kind of technology. And then take the diphenyl carbonate and working reaction with the diamine to making the carbonate and then pyrolyze it or making the polyurea directly. So in our study, we are trying to making the carbamic compound. And in the literature, we found benzoic acid is a catalyst. And we try to find, is there any other carboxylic acid is more reactive than the benzoic acid. But we found the changing of pKa value of different kind of acid doesn't do any help. And we also try to using different amount, and we try to using different combination of material. But what we found is by adding the benzoic acid, the amine compound, and that can catalyze the reaction much faster, and the lower the temperature also. And typically, we working on temperature in the melting of diphenyl carbonate, that is 90 degrees C. But then we found if we are using this combination, we can do it in the toluene compound, and then do the reaction on the compound, just preach it out of the reaction. And what we found is the amine compound, that oxydating compound, is because we're making the carboxylate and then making the anhydride compound. The anhydride facilitates amine carbonylation. And so we're making carbamate very, very mild, and then high yield, and then reaction without formation of the urea compound. The urea compound is affecting the pyrolysis compound, making the complicate our situation. So we can make the pure compound in better than 95%, and then we pyrolyze the compound making MDI. As you can see, the carbamate disappear, and the isocyanate becomes the major compound. And that is in 3 hours is done. And the compound, we frax it out of the distillation, can make it is about 80%. Actually, in the crude material, we can at least have a 90 plus reactions. And so we find that those descent is the best catalyst. That is aromatic compound, we found the aliphatic solvent is the best. The flushing out much faster. And the conversion rate is 100%. So on. And little CDI formation, usually the phosphate chemistry have this kind of compound. We don't have no chloride in the isocyanate. So if you are going to using MDI in a troubling compound, this will be the isocyanate for use. And then we are thinking, if we have this carbamate, and find out from this gentleman, you have reported the carbamate chemistry in the diamines can be trans-esterification easily, room temperature, 99%, very fast. And so we using this chemistry try to making the polymer compound. So what we do to making the polyurethane? Okay, okay. So using the carbamate compound, use as an intermediate, and long chain diamine, and short chain diamine, and long chain diamine of the diamine, and then we're making the polymers. And we can see the material we can make in high molecular weight, and is comparable to the polyurethane compound. And this is they have a very high recovery rate of phenol and TMS, and have a nice these elastomeric material. And then I try to go back to the aliphatic series. Aliphatic series is even simpler because the aliphatic diamine is even more basic. So replacement, making of carbamate chemistry is faster and more cleaner. And so without catalysts, we can do in room temperature. And, and this is what we do. You take in the diphenyl carbonate, in this solvent, a diamine, they precipitate out the compound and then pyrolyze in diphenyl carbonate. As I say, the aromatic compound diisocyanate, you're making the aliphatic the solvent. But the other way around is true. You're making the aliphatic isocyanate, you're giving diphenyl ether to the compound. So solvent selection in most of the compound is very important. Otherwise, you're using the polar solvent, then you'll be making the urea. You complicate your product. And so that is selectivity-wise is very, very, as I can show you, compound is precipitated out of the reaction, and the transformation is very, very, very quickly. And 98% precipitation. And if you pyrolyze this compound at 228 degrees, you can making the isocyanate compound easily. And we pyrolyze this compound, and you can see we have isolate after distillation 84% of isocyanate. So I think this is the way we are making the compound in different. And the last thing I can say is we can making the compound very easily, so carbamate can easily. So why don't using this one, and then do the transformation in the solution. We're one step making a polymer, because we so easily can make the intermediate in the situ. So why don't using one part, 2 step, 3 step, then making the polymer. And then we do the similar thing in the aliphatic system, and the compound can you can monitor the reaction. This is from carbamate, and to the carbonate to the carbamate, and then you go to the urea. That you easily can do, and so we can making the compound nicely and have a high molecular weight, and the method 4, that is 3-step reaction, the making carbamate, and then long chain compound, and then short chain, and then you fish out the big compound. So what I try to say is our process is very similar to the Asahi's process of making the diphenyl carbamate, making the non-phosgene PC. We are using the polyurethane, making polyurethane with the diphenyl carbonate. And I just want to skip all of this to the last page, I guess. They have no. This page, I just want to say, in this chemistry, we know it. So polycarbonate, Taiwan making a lot of it, and they have a lot of waste. Now we can, using this chemistry, can shifting the compound directly to PC and to making polyurethane. You're similar carbonate, so you can diamine, you can do that, and you can change it to a carbonate, and then using this part, making polymerization, and then using this part to do the polyurethane. Or you can use carbamate to making the acid by making polyamide compound. And we also making this compound. That concludes all my talk. I just want to show that who is making this compound happen. And 1, 2, 3, that is that person. I'm sorry, it's rushed it through. Okay.
Thank you. We'll take one question. If anybody has a question, we'll take one question. Up right here.
Did you try these thiocarbamates and go for
Which carbonate?
thiocarbamate instead of oxygen, sulfur?
No, we didn't. And what is the advantage?
Oh, is it thioisocyanates?
Oh, isocyanate. We didn't work on that yet. That is the area we from aromatic, aliphatic, and then maybe if your special case, then we can work on that. But we didn't work on.
Because you're working on cyanates, cyanates. Thiocyanate is potentially very useful intermediates in industry, pharma industry.
Okay. Thank you.